So what we have done is we are in collaboration with Freescale Semiconductor as well as this consortium called Semiconductor Research Corporation, where different semiconductor companies actually work in sync with the SRC guys, and we submit proposals to SRC and it gets funded by one of the semiconductor companies. So that's the history. So what we have done is we have created a portable runtime library based off of OpenMP for multi-core embedded systems. The target platform could be anything like Freescale's or Texas Instruments or Qualcomm's. So the idea is to keep the target platform as versatile as possible, as flexible as possible. So Sheng is the student who has been working on, it's a PhD student, and I'm from Dr. Chapman's group, University of Houston. So that was just a slide created to draw attention where all embedded system is used, be it home or be it, oh, didn't see that was going away. So yeah, so different places where embedded system is very prominent, and that makes it even more necessary to have a strong programming paradigm to program such devices. That's the Texas Instruments Embedded System Board, which is an 8-core EVM platform, and it's got several levels of cache as well, as you can see. This one is the Freescale's P4080 E500MC PowerCore processor, which we have used in our work. We have used a 2-core as well as an 8-core power processor for evaluating our work. That's a target platform. So if you notice, this board has a unique accelerator where it is pattern matching engine and SEC. It's not one of those usual accelerators that you would see. So these are very specific and tuned to run specific image processing applications or security based applications only. So that made our work a little bit narrowed down. So what I would like to do is a power processor plus DSP kind of a target platform. So because these are very unique and they are very specialized accelerators, programming them was even more complicated. They use something called DPAA, data path. I forget one is architecture, and I forget what is the other A standing for. So DPAA are super low level APIs, and you really need to know the architecture of PME and SEC if you want to program these accelerators. So the idea was, do we really want to go down that lower level and know the entire background of the low level APIs as well as the target platform to program these, or can we abstract all these details and go a level higher? Okay, so since you guys have a background of why we require better programming model, I wouldn't go deeper into it. So the idea here is you need to parallelize existing codes, you need an incremental migration path. That's where OpenMP comes into picture. And so you do these iterations, you keep plugging in certain pragmas, and you want to improve your code better, and so you go further make your code even more parallelizable. And you want to exploit multiple levels of parallelism. Again, not all programming models are equal, none is perfect, and that's where we need to use the industry standards. That's where you want to be able to create one level of programming model, one unified layer, and be able to target more than one kind of platform underneath. So in order to do that, we chose OpenMP as our starting point. Again, I guess you have good background, you know what is OpenMP. So I just have the slide to say from its inception until today, how far OpenMP has gone. And I highlighted this word portable because that's the key word when you use this OpenMP model for an embedded platform, and that's the sole purpose why we are using OpenMP. Portable. So we want to keep the code as portable as possible to target more than one type of platform. Okay, so we have OpenMP, it works for shared memory processors. We have 4.0 where you have the vocabulary for accelerators, etc. So what we're trying to establish a connection between what OpenMP can do and what embedded system requires. So for example, we want to be able to concentrate on the algorithm itself and not on the lower level details of concurrency, which is an important factor for embedded system itself. And OpenMP runtime relies on lower level components such as threading, OS, and etc. But sometimes you don't have an OS at all. So how would you actually use OpenMP on a bare metal platform? And embedded system typically lacks some of these features. So what do you do then? Does OpenMP have that vocabulary? If not, how you can facilitate and use OpenMP on embedded platforms. So yeah, so vocabulary for heterogeneity required for the embedded space. So what we do is, that's the programming stack that we have worked on. We start with OpenMP applications and we create a translation of OpenMP to these APIs. Now this is when Sven is going to give you a much more elaborate idea of what these APIs are. And R here stands for resource management, C is communication, and T is task management. These belong to MCA APIs, which is again an industry standard put together by a lot of semiconductor industries for the sole purpose of creating an industry standard for embedded systems. So what we do is we create a translation between OpenMP and this, and we bypass all sorts of lower level details of the embedded platform, and we use our translation layer directly on the device itself. So that's where the implementation itself comes into picture. So translate OpenMP for MP socks, and we use the MCA APIs as a target for our translation. And we wanted to keep it lightweight, which is the key idea when you want to target an embedded platform. Supports non-cache coherent systems, which is again a vital point. And performance, what we do is we compare our performance to a proprietary vendor-specific implementation to evaluate where we stand and in what we have done. And the results were pretty cool. That's the compilation process. So what we do is, I'm from University of Houston, and we have an open source compiler that we use, OpenUH, which is a front end source to source compiler. And this is downloadable from our website, and there is an email ID if you want to ask if you have any issues with downloading and using it, contact us. It's GCC based. It's a branch from Open64 itself, University of Delaware, that's where it started. So what we do is we create multi-threaded applications out of a C code. Like we take a C code, put in OpenMP pragmas, create a parallelized version, and that's our starting point. So that's app.c, like a test code. And we translate that into the intermediate representation of OpenUH, which we call the W2C. OpenUH has 5 different levels of intermediate representation. The idea of using OpenUH was we wanted an IR which is closer to the source code than to the lower level code itself. So that's where the translation becomes a tad easier. So we use the intermediate representation of OpenUH, and as for backend, that was the PowerPC GCC provided to us by the Freescale Semiconductor guys. We use that to generate the object file libraries, and here is where we create a link between the OpenMP runtime as well as the MCA build libraries. And the target platform, we started with the dual core power processor, the IBM power processors basically. The board is belonging to Freescale Semiconductor, and we've moved on gradually to an 8-core, which showed that the implementation that we created didn't quite break, or it was scalable to more than 2 cores. So that's a case study that we used. So we have considered applications from MyBench, which is an embedded benchmark suite, and we have also used applications from Rodinia, which is a heterogeneous benchmark suite, mostly meant for CPU, GPUs, but we used some smaller codes that was usable for embedded systems. So Dijkstra is from MyBench, embedded benchmark suite. That's the OpenMP version for you. And that's a translation of OpenMP using OpenUH compiler. So intermediate representation, we call that intermediate representation as W2C. W standing for World 2C. And so this is comprehensible, and if you go levels down, few more levels down in the compiler, it becomes beyond comprehension, at least to me. I'm not a compiler person, more of a runtime person. So that's a translation of the OpenMP itself. You can see OpenMP fork and number of threads, and W2C is again your intermediate representation. And so what we do is we try to insert the MCA routines. Like you can see the MCAP initialize. So MCAP APIs have these node attributes, like you can define the domain, the node, and the topology of your architecture itself. So the number of CPUs which we want, and yeah, right. So all these are again how we try to include the MCA routines within the, we call those MCA routines within the translation itself. that is the definition of the OMPC fork, and again you see that we have there is a status and there is all these node IDs. This implementation is based off of the resource management APIs of MCA. Like I said, there is communication as well as task management, and that's ongoing work so far. Then in the make file, this is just to give you an idea, the process that we take to compile our code. So you see that we have linked the MCA build libraries to our OpenMP build library itself. And so Dijkstra, and yeah, so those are the steps for compilation itself. And the result wise, we named our portable runtime that we created as libeomp, where E stands for embedded. And this is just to keep it in parallel with libcomp, GNU-based OpenMP runtime library. With one thread, you initialize the MRAPI, etc. That's your execution time. And then you use the 8 cores. I'm talking about 1 core and 8 cores of the Freescale 8-core power processor board. And we see that the time obviously reduced from 10 to 1. So this slide actually shows how the evaluation of our libeomp on several applications. The takeaway from here is that's the proprietary customized runtime library from Freescale, and this is ours. So you see that there is no overhead that we incurred due to the translation process. And the execution time wise, we didn't do better than libcomp, but we didn't do worse either, which was good news to us, because we could go back and change the algorithms and make the execution time go lower than the libcomp itself. And we used EPCC microbenchmark suite to measure the overhead of our implementation, and that's where we figured that, oh, barrier algorithm wasn't doing as good as it was supposed to do, so change the barrier algorithm, and we used a tournament barrier algorithm which did better in terms of overhead measurement. So here you don't use the proprietary runtime library, you don't do the low-level coding, you don't need to know the underlying architecture. You simply take an OpenMP application, use the portable runtime, which is libeomp, target a Freescale, and you still almost get similar performance to what the harder way of implementation you could have taken. So what we are trying to say here is you achieve portability to a good extent, scalability to what extent. This is from 2 cores to 8 cores. So we do not lose anything when we when we did a transition from a 2-core to 8-core. What we would want to do is try and target heterogeneous platforms, like imagine you have a Nucleus OS and an Android OS. So again, that is a vocabulary for heterogeneity. How would you create this unified layer to target more than one type of OS, leave alone devices from different families? And if you take Texas Instruments, for example, they have this 48-core DSP. So will libeomp, how much effort do we need to put to libeomp to target a platform that is not Freescale? So that we are in the phase of finding all this out. The board that we targeted was the P4080, where I showed you those PME and SEC accelerators, which were quite tricky to use. So and that didn't really help me generalize the runtime itself. So I would want to move towards a power processor plus DSP, which is traditionally the kind of multi-core that you would use. Yeah, that's what I got. That's. So in the previous slide, so this one I'm showing the scaling and not the actual execution time, you're right. The idea here was to, the concentration here was to show the scalability. I see what you're saying. The slide doesn't show quite that. We started from a 2-core, like I said, and I wanted to show that, well, we didn't have to do anything much to our libeomp to use an 8-core platform. So that was the focus. And later, if we want to use like 16 or 48 cores, we want to make sure that the scalability is still maintained.
How does the actual wall clock performance compare to
It was the actual wall clock performance. So the actual performance time of the wall clock time of libeomp compared to that of libcomp. So it was almost the same, except for certain applications. Okay, I'll take a step back. So the implementations that used parallel and barrier, we did better than libcomp by a fraction, not too much. That is because the EPCC microbenchmark suite helped us improve the algorithms. We found there were a lot of overhead. So we changed the barrier algorithms and the tournament did better. But stuff like single and critical, we have not done better compared to libcom. Again, the execution time is not bad at all in comparison. It's a fraction bit bad. So I would need to see what happens to my time when I use a different board or use more cores. That's where the challenge is, I think. Any more questions? The flyers that you have has the MCAP and the MTAP APIs, it's reference cards. We do not have one for MRAP per se, but if you go to the MCA website, MultiCore Association website, you can download the prototype implementation of MRAP, MCAP, as well as the 150 pages of API description itself. So I will hand it over to Sven, who is from PolyCore. So Sven and Marcus, who is the founder of MCA, we interact quite often to try and figure out the gaps in MCA and how to fix the implementation as such. So that's where we got in touch. So I'll give you this first.
I asked you to switch to, yeah. Yeah. Is that good? Okay. All right, so I'm going to talk about the MultiCore Association, which is what University of Houston is basing their OpenMP implementation for embedded systems on. So, I'm a board member and co-founder of the MultiCore Association, and I'm also the chairman of the MCAP working group, which is one of the working groups. And embedded systems, they span the industry from, like we have here, high performance computing to very, very small devices that go at very, very low speed. And they almost always come in different shapes and forms. So my cell phone may not be the same as yours. So, and they may have different processors, accelerators. So there is a large variety, and they increasingly contains multi-core. And if you look at the space that's closest to high performance computing, so telecom, datacom, they have been around for a long time, but we see them in the smallest devices where you actually wouldn't think of it. And so they're creeping in everywhere. And obviously performance is a key driver for multi-core. Another one is power consumption. So you know, I think this one has a quad core, but a friend of mine has told me, who's in this business, he said they're rarely all four going at the same time. So you clock them down or you shut them down. So thereby you save, but you have the performance when you need it. And actually, you can get the same performance at a lower rate than you can with a single processor. So this trend is just going more and more and more. And obviously also consolidation, where you have a rack today and you want to bring it to a board and maybe to a chip. I mean, if you look at HP, they're advertising the Moonshot, which is where they took lots of blades and put them in one. And we're also seeing where you have 2 or 3 products that you want to now make one product. So it could be an analysis product that you can couple with a control product, and so it may be multiple processors that could be on different chips or in the same chip. And so that creates a lot of challenges. So we have an enormous array of possibilities. So Sunita talked about some of the TI chips and the Freescale chips, and they come with processors, some of them have CPUs and DSPs, and they have a plethora of accelerators, and they may have different memory architectures. Sunita talked about cache coherency or not, and you have local memories and shared memories and so forth. So the number of variants is enormous, and you have to look at how do you program these devices with multiple cores, different types of cores, different operating systems and so forth. And you absolutely need the portability and the scalability, so you have to, your same application needs to be able to run on 2 cores or 16 cores, or if you have a RISC processors and you have DSPs, you can't afford to rebuild your application every time, because most applications today, they just get bigger and bigger and bigger. And so you have to find ways to portably move your applications to a variety of platforms. And obviously concurrency and parallelization comes in different shapes and in different granularities. So you may have a parallelized arrays, or you may have much bigger chunks where you have tasks that are parallel and they interoperate. And obviously we have virtualization in some systems, and in others we don't. So the MultiCore Association was established in 2005, and the purpose of the organization was to enable the multi-core ecosystem to make it easier to use multi-core. And we have membership across the globe, and it's a committee-based standards development. We have working groups, and anyone in the organization can join a working group, and so it's all volunteer work. And we focus in several different areas. We started here with the foundation APIs, and those were the ones that Sunita talked about. So it's a communications API, it's a resource management API, and it's a task management API. And then we have provided a programming guide, and we have, I don't know what. Okay. And we also have, more recently, we have started a group that works on software-hardware interfaces. So, for example, when you have a processor that has 10 hardware accelerators. So, I have a different hat that I run a business, and we are in the multi-core software business, and we support different devices. So, our engineers, they may have to read manuals that are hundreds and sometimes thousands of pages to figure out how a device works. So what we're doing here is we're working on a way to describe the devices in a standardized way, so the vendor can describe their device, and my company's tools or anyone's tools can read this information in a standardized format. So instead of reading 1,000 pages, we may only have to read 10. So we can more quickly support those devices. And we're doing some other things too, but I'm going to go somewhat quickly here. And so again, the target domain is embedded multiprocessing. And we refer to it as closely distributed computing. So we're not really in the widely distributed where you have tons of computers in different locations. It's really more on a chip or on a few chips on a board or in a rack, maybe. The assumption is that it's a system that is there all the time. You may have power down and power up, but the same number of cores are there every time. And it targets homogeneous or heterogeneous systems. And do you have a question? Not yet, but it's going there. So yes. So the question is: is the are embedded systems in the thousands of cores, and I would say today not really, even though I have actually seen one, a military system that had over 1,000 DSPs. So, but I think that's not so common. But we're on a system today that has 64 cores. It's an embedded system, but the whole idea when you create a standard, you can't focus on only what's there today. You have to think, will this standard work, in 10 years from now? And also very important to allow implementations that are possible in resource-constrained systems and where you have real-time requirements. So, we are in some big systems, and we're actually now looking at going into a system where we may have a few kilobytes to work with. That's it. And also, it's very important that the standard provides an incremental migration path. So it's very rare that you start application development from scratch today. You typically take whatever you had in the previous generation and you transform it to the next generation. And again, different granularity of parallelism. So we currently have these working groups, so the Communications API, and we have produced version 1 and today version 2. So version 2 came out 2.5 years ago. Programming practices, we have the first guide, and we're now looking at version 2 there. And resource management in the version 1, and then we have software-hardware interface. This is a recently started group. Task management has also produced its first standard. And these three, the communications, resource, and task management APIs, those are the ones that Sunita efforts are focused on. And we also have a tools infrastructure and virtualization group. And so the primary beneficiaries of standards, or at least these standards, are the users of the systems, or I should say the OEMs and the ODMs that produces devices. They can more easily get to market. They will have better availability of tools and more portable applications. So the whole idea is to make it easier and provide for a better ecosystem in the multicore. And then, of course, the other side of the coin is that the vendors providing tools like my company does, or the chips or operating systems or middleware, they can take advantage of these standards as well, because you have fewer variants to support if you have a standard. So if it's completely freeform, it's a lot of work. If you have some interfaces that are in between your value add and what's underneath, it makes it easier. So a little bit more about MCAP. So MCAP is the MultiCore Communications API, and I can't think of any system today that has more than one course where you don't need to communicate. You can do it in different ways, but you can't live without it. And MCAP has three types of communication. It has connectionless messages, connected packet channels, and connected scalar channels. And messages and packets are buffered communication. Scalars are obviously scalars. And we also provide some functions to create and manage nodes and endpoints used for the communication. And the message passing has inherent synchronization, and which works as well in SMP environments and AMP environments. So and obviously it can be compiled by any standard C compiler. So the whole idea is that you can use this in pretty much any environment that you can think of. It can. So you can go out and find out what else is available in the topology. So an MCAP topology contains that it has domains, nodes, and endpoints. That's what an endpoint is defined by domain, node, and endpoint, or a port. So what you can so it's a statically defined topology, at least within a domain. So you can go out and discover what other nodes are available and endpoints in the topology, and then you could do a secondary discovery to find out what are the capabilities of those nodes. Okay. And MRAPI, that's for, again, resource management, so it provides basic synchronization and locking. And ability to manipulate shared memory and remote memory meaning something that you don't, it's not a memory that everybody can see. It could be, for example, through another device. And also has some functionality for accessing metadata in the system. So if you have performance counters and so forth, they can be queried through the API. And the task management API obviously has to do with tasks and how you can execute tasks on different cores, and they don't have to be of the same kind. They can be different kind, and they can be accessible locally or through some other device. And it's very similar to any task that you think of in the general sense. You pass, but in this case you pass parameters to wherever the task is located, and it will return a result. And then the shim, that's the software-hardware interface, and again that's a way to describe hardware by a hardware vendor that can be used by a tools vendor to more quickly add support for whatever their hardware is. So you can use it for manipulating the device, or you can use it to get performance data out of the device, for example, memory bandwidth or something like that. And this is a more recently started effort. And here's just an example of a tools being used for MCAP in this case. So the tools basically provides an abstraction, automation, and portability. So by using tools to help you to implement the MCAP, MTAP, and MRAPI, you can completely focus on your application code and not worry about how this applies to the underlying platform. So in this case we have a tool that you can use for MCAP coding. So the tool will ask you what do you want to do, and in this case I think it's a MCAP message, and you can select, we have blocking and non-blocking, and then it will give, and then you say I want to communicate to this node, and then it will give you all the available ports on that node, and then when you say okay, then it will actually insert the code for you. And again, as I said, this is a worldwide organization, and we have the organization started mostly with what I would call providers, and now we have both providers and consumers, and obviously the consumers are the main beneficiaries of this. So that's it. So any questions?
You send tasks across the network to other nodes.
Yes.
Presumably functional tasks.
Yes.
Do you have some sort of provision for tasks with side effects to be distributed, or is that something that simply doesn't apply?
So can you repeat the question? He's recording. So the question was when you
send tasks across the network,
yes.
do you have some sort of provision for tasks that have side effects, or is that simply something that doesn't can be parallelized?
Okay, so the question was if we can send tasks across a network that has side effects, and I unfortunately I would have to get back to you on that because I don't know the answer. So I have been involved in two of the other groups, but not the MTAPI group.